problem set number 4 in this video, which is dealing with atoms and really getting into the nitty-gritty of what makes up atoms. So this first part is filling in missing information about atoms of the 8 nuclides in the following table. Basically, we've got 8 elements here, and we need to figure out information about them. So what I'm going to do is I'm going to split my screen with the periodic table, because that's where we're going to get most of this information, and we should be familiar with how to use it. So first, in the first one, they give us the symbol sodium 23. Sodium is right here on the periodic table. That 23 refers to the mass, which is protons plus neutrons. The symbol here tells us that number right there, 11, that's the atomic number, okay, and that tells us the number of protons. So sodium is always going to have 11 protons. Then it asks for the number of neutrons. Well, the mass of 23, sodium's mass could change, okay, but it's always going to be protons plus neutrons. So if we know the protons, then we can find the neutrons. Oh, I don't know where that 22 came from. 12. Right, so then we're asked for the number of electrons, and the number of electrons is going to be equal to the number of protons as long as this this atom is neutral. So if we've got 11 protons, then we're going to have 11 electrons. And lastly, it asks for the mass number, which again is protons plus neutrons. It's given right there. So 23 it is. Right, so let's keep going. And the second column gives us the number of protons. Well, again, the number of protons defines what the element is. So I just go here on the periodic table. I find 39, which is this Y right here. So I know that this must be Y, which I guess stands for yttrium. Right, 39 protons, and then it tells us there's 50 neutrons. Well, if it's neutral, then we know it will also have 39 electrons. How do we know it's neutron, or how do we know it's neutral? Because it just says nuclides. You'll look at this next one, it says ions, which means they're all charged. But in this part A, these are all going to be neutral. So we know it has 39 electrons. What's the mass number? Well, the mass number is protons plus neutrons, so in this case 89, so really we could put a little 89 right here. Hopefully you get the hang of this pretty quick. I'm going to start moving through them pretty quickly. So we know protons and electrons equal, so that's 50. If the mass number is 118, then this must be 68. And if it's 50 protons, then periodic table says it should be Sn, which is 10. So we're going to have Sn 118. Here, 79 protons is gold. Mass number of 197. That means I've got 79 electrons, and I have 118 neutrons. Okay, aluminum 27 must have a mass number of 27, and it's aluminum, so it has 13 protons, 13 electrons, which means it must have 14 neutrons. 42 is molybdenum. And if it's got 56 neutrons, that means it has a mass number of 98. 42 electrons, because that's the number of protons. 98. Alright. 60 protons, which means the number of neutrons is 83. And so 60 protons will be, where is it? Down here, Nd 143. And then here we have 92 protons, which is uranium 238, which means it's going to have 146 neutrons and 92 electrons to match the protons. Alright, B here is asking for information about ions, which means they're going to be charged. So here, the number of protons is, for chlorine, is 17. which means that we've got 20 neutrons to hit the mass number of 37, and then because it's negative, that means it has an extra electron. So instead of having 17 electrons to match the protons, we'll have 18 electrons to make it have a 1 negative charge. All right, 11 protons is sodium. And then because it also has 12 neutrons, the mass must be 23. And then because of 11 protons and 10 electrons, this is actually going to have a positive charge because it's deficient 1 electron. Okay, mass number of 81, 46 neutrons, means we have 35 protons. 35 protons is bromine. And if you have 35 protons and 36 electrons, it's actually bromine minus. 88 protons will be radium. You know, it's 226 because they give us the mass number. Number of neutrons is the difference between those, the mass number and the neutrons. So that's going to be mass number of the protons, so 138. And then 88 protons, 86 electrons means we're deficient 2, so that's a 2 plus. Barium 2 plus 137. All right, they give us the mass as 137. Barium tells us that the number of protons, the atomic number, is 56. And then from those two, we can find the number of neutrons, which is 81. And because it's 2 plus, we're missing 2 electrons, so we must have 54. 30 protons will be calcium, with 34 neutrons, gives us a mass number of 64. Like today. Oh, yeah, 30 protons. Oh, that calcium's 20 protons. 30 protons is not calcium, it is zinc. With my 34 neutrons gives me a mass number of 64. 30 protons, 28 electrons, means that we have a charge of 2 plus. Perfect. 16 neutrons and 32 mass number means 16 protons as well, which will be sulfur with 2 extra electrons, so that's going to be a sulfur 2 minus. And then we've got 40 protons, which is zirconium. Must have 50 neutrons to add up to the mass number of 90, and then we're deficient 4. So it'll be a 4 plus. Hopefully that process makes enough sense. Bring this back to full screen. All right, in 1 to 3 sentences, define an isotope. An isotope is 2 atoms of the same element, meaning they have the same number of protons, but they have different masses. The only way that you could be the same element and have different masses, that suggests that you have a different number of neutrons. So isotopes are atoms of the same element with different masses are called isotopes. Explain the redundancy in the nucleide symbol. Oh, that did not turn out very well when I transferred it into OneNote. So what this should say is X, A, Z. So X, as we can look up here, X is the atomic symbol, the element symbol. A is the mass number, and Z is the number of protons. Well, this is redundant. That's why we haven't written here. It's redundant because if I know the element, then I know the number of protons. I don't need you to tell me both of them because they literally tell me the exact same thing. So that's redundant. Write the symbol of the most abundant isotope of sodium. How many neutrons does it contain? All right, let's jump back over here. Sodium is Na. So Na, how do I know what the most abundant is? Well, if you look on the periodic table here, this gives you the mass of 22.99. That is a weighted average of all the different isotopes of sodium that exist on Earth naturally. Because it's a weighted average, those isotope masses that are most common will pull the average closer to them. So if you're ever asked a question like this, best way to answer it is just look at the periodic table. 22.99 is very, very close to 23. So sodium 23 is likely the most abundant isotope. How many neutrons does it contain? Well, it's sodium, so it's got 11 protons, which means it must have 12 neutrons. All right, moving on. And these problems will probably reference the periodic table moving forward, but I won't necessarily pull it up every time. Okay. So, helium balloon you got on your birthday is almost entirely deflated, but there's still a very small amount of helium-4 inside with a total mass of 160 mu. How many protons, neutrons, and electrons are present in the balloon? All right. AMU, what is AMU? That means atomic mass unit. That is like roughly we could say a proton and a neutron each weigh 1 AMU. So protons 1 AMU and neutrons 1 AMU. So if we have helium-4, one atom of helium-4 weighs 4 AMU, and since it's helium, it has 2 protons, which means it must have 2 electrons. So that means if we have 160 AMU, half of that is protons, half is neutrons. A different way to write that is if we have 160 AMU, I know that one helium-4 atom has 2 that one proton is 1 AMU and that there's 2 protons in one helium-4 atom, which means I know that we have 80 helium-4 atoms. It's kind of a roundabout way, but if we have 80 helium-4 atoms, then we know we have 80 protons, 80 neutrons, 80 electrons. How many neutrons are there in 10 grams of fluorine-19, the only stable isotope of fluorine? Well, my starting value is this 10 grams of fluorine-19, and I want to know how many neutrons there are. Well, because we haven't talked about moles yet, I am going to do this in atomic mass units, this AMU. What you need to know, do they tell you here? No, they don't. So what you would need to know to answer this question is that 1 AMU equals 1.6605 times 10 to the negative 24 grams. Because then what I can do is I can say I know that 1 AMU equals 1.6605 times 10 to the negative 24 grams. Now I'm in units of AMU, and I know that 1 neutron weighs 1 AMU. The problem with this, though, is that this is what I should do. I should say that 1 atom of fluorine-19 weighs 19 AMU. The problem with what I was doing before is that it was assuming that all the 10 grams were neutrons, but they're not. But we know that all the 10 grams is fluorine-19. So now I know how many atoms of fluorine-19 I have, and then because fluorine has 9 protons, we know that 1 atom of fluorine-19 has 10 neutrons. plug that in. That should give me the right answer. How many signifigs can I have? I can have 2, so I would get 3.2 times 10 to the 24 neutrons in 10 grams of fluorine-19. Calculate the number of neutrons found in 2.13 milligrams of the non-fissionable isotope of uranium, which has a mass of 238. All right, so what's my starting value? 213 2.13 milligrams of uranium-238. And I'm trying to get to neutrons. Very similar to the last problem. Take my mass and get it to grams, because I know there's 1,000 milligrams in 1 gram, and I can use that AMU conversion of 1 AMU is 1.6605 grams, right? Yep. Oh, times 10 to the negative 24. Now I'm in AMU. I know that 1 uranium-238 weighs 238 AMU. And then I know that 1 uranium-238 is going to have a certain number of protons in it, or of neutrons in it. I think we actually did that one up here, didn't we? Uranium-238 has 146 neutrons. So I plug it in my calculator. And with those 3 significant figures, I get an answer of 7.87 times 10 to the 20. Perfect. Okay. Pencil lead. Pencil lead is actually a form of carbon called graphite. If a single carbon atom has a diameter of 1.54 angstroms and 10 angstroms is 1 nanometer, how many carbon atoms could fit side by side along the width of an exclamation point line drawn by your pencil? Assume pencil uses lead that is 0.2 millimeters wide. This is very similar to a problem that we did in problem set number 3. But what is our starting value? What is the actual amount of carbon that we're dealing with? Well, that's this 0.2 millimeters wide. We have other numbers in here, this 1.54 angstroms, but that's just a conversion factor telling us 1 atom of carbon equals 1.54 angstroms. And we have this, which is also a conversion factor. So if we want to get to carbon atoms at the end of the day, we know if we can get to atoms if we can get to angstroms, because we have a conversion factor there. Get to angstroms if we can get to nanometers. So let's try and get to nanometers. Now you could go straight to nanometers, but I'm going to go through meters first. And then I know 1 meter is 10 to the 9th nanometers. Then I've got these other 2 steps here. 1 nanometer is 10 angstroms. And lastly, there's 1.54 angstroms in 1 carbon atom. Just like that, we've converted our length of 0.2 millimeters into carbon atoms. And with how many significant figures? 3 significant figures? Nope, 0.20, 2 significant figures. I get 1.3 times 10 to the 6th. It's kind of cool. Over 1 million atoms of carbon across that pencil lead. Alright, how many protons would be in this line of carbon atoms? Well, this should be pretty easy. If we know that we have 1.3 times 10 to the 6 carbon atoms, and carbon is defined by the fact that it has 6 protons, then we can say one carbon atom has 6 protons. So we can just multiply that number by 6. 3 times 10 to the 6 times 6. Oh, sorry. 1.3 times 10 to the 6th times 6. And that gives me 7.8 times 10 to the 6th protons. Awesome. Alright, last one here. A single gold atom has a mass of 197 AMU. How many gold atoms are in a cube of gold that's 10 millimeters on each side? About the size of a sugar cube. If the density of gold is 19.3 grams per centimeter cubed. Here's that AMU conversion that I used before. Okay, another unit conversion. What's our starting amount? How much gold do we actually have? Do we have 197 AMU of gold? No. That's how much gold is in a single atom. Do we have 19.3 grams of gold? No. That's how many grams of gold are in 1 centimeter cubed of gold. How much do we have? We have a cube that's 10 millimeters on each side. Well, if it's 10 millimeters on each side, 10 times 10 times 10 means that it is 1,000 millimeters cubed of gold. I just did the geometry to say I got this cube, it's 10 on each side. So if I want to know how much I have, 10 times 10 times 10. 1,000 millimeters cubed. Well, I'm trying to get to what? Gold atoms. I know that one gold atom is 197 AMU. Right? So if I get to AMU, I can get to gold atoms. I can get to AMU if I first get to grams. Okay, and I know that I can get to grams if I get to centimeters cubed. So I need to get millimeters cubed to centimeters cubed. Let's show you how we're going to do that. First, I'm going to go from millimeters cubed to meters cubed. Now, I know that there's 1,000 millimeters in 1 meter, but that does not mean that there's 1,000 millimeters cubed in 1 meter cubed. That is not true. Okay, because this is volume and this is length. So I could just Google millimeters cubed to meters cubed, and Google would tell me that there's 1 billion, 10 to the 9th, millimeters cubed in a meter cubed. But I don't always have Google available. But I do know that there's 1,000 millimeters in 1 meter. So if I want to cube the units, all I have to do is cube the numbers. So I know there's 1,000 cubed millimeters cubed in 1 cubed meter cubed. That's just taking a length conversion I know and generating a volume conversion from it. Alright, so I want meters cubed on the bottom. I got to get to centimeters cubed. I'm going to do the same thing. I know there's 100 centimeters in a meter, so there's 100 cubed centimeters cubed in 1 cubed meter cubed. Now I'm in centimeters cubed on the bottom, and I have this conversion of 19.3 centimeters cubed, oh, that's not true. I have this conversion of 1 centimeter cubed to 19.3 grams of gold. Now, since I'm in grams, I know the conversion from grams to AMU is 1.6605 times 10 to the negative 24 grams in 1 AMU. The last step to get to gold atoms would be to know that 197 AMU makes of 1 gold atom. So doing the math quickly, and when I I did that with, let's see, 3 sig figs, 3 sig figs, 3 sig figs. So my answer is going to have 3. And I got 5.90 times 10 to the 22 gold atoms. There we go. So that is problem set number 4. Kind of breaking down something about the atoms. Now I know we used AMU a lot here. AMU's useful, but once we get over here to problem set 6 and we start talking about moles, we really won't use AMU much anymore. But there you go.